2.4 on evaluating logarithms and graphing logarithmic functions. So we spend a lot of time in algebra talking about inverse functions and paired functions. What are operations that are opposites of each other? So the first 3 lessons talked about exponential growth, exponential decay, exponential functions. This is going to be the opposite of that. Logarithmic functions are the opposite of exponential functions. They're inverse operations. That's going to be important later. All right, I'm going to go ahead and expand out this window so it makes it a little easier for us to see some of the things we want to work with. All right, so some of the examples we're going to see, again, not so much in the lesson video, but in the word problems, in the textbook, how are we using this in real world? We use logarithmic functions to talk about tornadoes, altimeters, and chemistry. We use this quite a bit in chemistry. So maybe you'll see some of this later in your chemistry class. Okay, our next slide is pretty important. You may want to pause this so that you can copy down some of this important information. Maybe wait until I finish speaking, then pause it for a moment before you move on. I'm going to try and use the highlighter here for this one. Okay, so the key concept about logarithmic functions is this. If b and y are positive numbers and b can't equal 1, then the logarithmic the logarithm of y with base b is denoted by log by. All right? Kind of a highlighter there. So log base b y. And so what this means for us is this right here. Log base by is equal to x if b to the x power is equal to y. So let's give a quick example. We're going to have some examples here in just a minute, but to give you an idea, if I say log base 2, 8 equals 3. That means 2 to the 3rd power, here's b, here's y, I'm sorry, here's x, is equal to y. 2 to the 3rd power, 2 times 2 times 2 is equal to 8. So this relationship right here is very important. You may want to put on your paper somewhere a sticky note or a note card that you have out with you at all times when you are working on logarithmic functions. This relationship, this log base b y equals x, and to rewrite that in exponential form, b to the x power equals y. These are equivalent functions. They're inverses of each other. So, why do we need to know about logs? Well, I have an exponential function, and I need to solve for x. I need to figure out what is that exponent. I can't take the root of it. This is not like x squared. This is more like 2 to the x power. How do I figure out what x is? So we're going to talk about some ways of doing that. A couple of other terms you want to be aware of, and you'll notice this when it comes to your calculators, is what we call the common logarithm and the natural logarithm. All right, the common logarithm is base 10, and usually you'll just see the question like this. All right, what's the log of 32? If you don't hear them say log base whatever, they just say what's the log of and then the number, then that means the base is 10. We don't write it, but really the base is 10. So we're trying to figure out 10 to what power equals 32. We know from our powers that 10 to the 1st is 10 and 10 squared is 100. So x is somewhere between 1 and 2, but without a calculator, how do we know what it is? And then we have what we call the natural logarithm. So we had exponential functions that had the Euler number e. So now the natural logarithm is basically the log, but the base number is e. So instead of saying log e, we just rewrite that to say ln, the natural log. All clear this up and move on to our next slide. Probably only going to get through a couple of slides. It takes a while to talk through some of this stuff, so this lesson may take a couple of videos, 2 or 3 videos. I'm not really sure yet. We'll see how it goes. All right, so our first example is how are we going to rewrite this so that we can get familiar with the process of knowing how to solve it. I'm going to change out the color. I don't like that green. Let's go with blue. I like blue. All right, so our first example is log base 2 of 16 is equal to 4. So to rewrite that, this is my base number, this is my exponent, and then the solution is 16. And we want to double check. Does 2 times 2 times 2 times 2 equal 16? Because if it doesn't, then this is not an equivalent equation. But of course, these are all going to equal that. That's why they're examples. All right, so take a look at example B. Log base 4 of 1 is equal to 0. Well, 4 to the 0 is equal to 1. This is our base number. Remember when we have exponential form, you have your base number, you have your exponent, and then you have whatever it equals. Sorry, I'm getting my letters confused. B to the x is equal to y. So 4 to the 0, anything to the 0 power is 1. We know that. All right, so base 9 to the first power is equal to 9. Here's where it starts getting a little tricky. If they're not even numbers, if they're not whole numbers, let's take a look at what happens when we have fractions. All right, so my base number is a fraction, 1 over 5. Not necessarily important just yet, but it will be important in a second. Remember that 1 over 5 can also be rewritten as 5 to the negative 1. Remember, negative exponents do not make the number negative. 5 to the negative 1 does not equal negative 5. Still seeing that on some of your quizzes, so be careful with your negative exponents. It just means you make the inverse. So turn it into a fraction. Move this to the denominator. Okay? So 1/5 to the negative 2 is equal to 25. And you may be asking yourself, well, how does that make sense? Well, remember that negative 2 tells us to flip. So 1/5 flips to 5. So then instead of saying 1/5 to the negative 2, now we have 5 squared. And we know 5 squared equals 25. So that's why it works for us. All right, so let's move on. Evaluating logarithms. Now for this slide, these examples are going to be done by hand. So we're not using our calculator yet. When I get into the next slide, I'll explain to you why that is. Do a quick check on the time. Well, get my pen set up and then I'll do a quick check on the time. Oops. It's got to be a mouse to do that. You guys can't see the timer when I'm recording, but I can. And I want to make sure I don't run over. There we go. Okay, so we got a couple more minutes left. It's 8:57, 9 minutes now. So I want to make sure I don't go over on that. So let's go back to the big screen, and then we'll pause after this point. Like I said, this may take us a couple of slides to go through, a couple of videos to go through. Okay, so for evaluating the logarithm, we want to figure out basically what x is. So we're thinking to ourselves, okay, 3 to some power is equal to 81. Again, right now, these are examples that you can do with mental math. So think to yourself, 3 times how many times of 3 would equal 81? So if you go through the process, 3 times 3 times 3 times 3, all right, that's 3 to the 4th power to get to 81. So that means x is equal to 4. So your solution here is 4. Okay? Example B. Log base 4 of 25 hundredths is equal to what? Now for me, it helps if I remember that 25 hundredths is also the fraction 1/4. So if I have a 4 here in the denominator, and I know that I can rewrite that to 4 negative 1 because my base is 4, if I can rewrite that to something equivalent, that's going to help me get closer to what x needs to be. Well, now that my base matches what it's supposed to, matches that 4, I know that x is equal to negative 1. And again, you can always check your solutions. Does 4 to the negative 1 equal 25 hundredths? All right, well, negative 1 means 1 over 4, and of course, 1/4 is equal to 25 hundredths. So yes, it does work out. All right, example C, 1/6 log base 1/6 of 36 is what? So that means 1/6 to some power is equal to 36. Well, we can already tell that I need a bigger number. I can't have an even number, or sorry, a positive number for my exponent, because that would be 1/6 times 1/6 times 1/6, which means my fraction is just going to get bigger and bigger and bigger. So I know that that 6 needs to become positive. I'm sorry, not positive. That 6 needs to become, instead of 1/6, it needs to become just plain old 6. So that means the exponent's going to be negative. So let's change that to 6 to the negative x is equal to 36. All right, well, what would make 6 36? Well, 6 squared is 36, but I had 1/6, so in order to get positive 36, I need to have a negative exponent. So if I were to go and solve this, what does 1/6 to the negative 2 mean? It means 6 squared, which means 36. So again, a lot of this right now is going to be kind of some mental math. And you're having to really, verbalize, whether in your head or out loud, what your steps are to justify your solutions. All right, let's clear off the board so we can see my last example. Okay, so log 27, log base 27, I should say, to some power is equal to 3. Well, again, we're going from a big base to a small number. So that tells me that x can't be a positive whole number because I'm going to end up with some crazy fraction. Or sorry, not crazy fraction, some crazy big number. 27 to the first, 27 squared, 27 to the third. All right, that's not getting us anywhere near 3. And because 3 is not a fraction, we know that x is not a negative number. So x isn't a positive whole number, and it's not a negative number, so that tells me that it actually is going to be a positive fraction. So we already know that there's a relationship between 3 and 27, right? 3 times 3 times 3 is equal to 27. So that means that the cube root of 27 is equal to 3. So if I want to write a root as an exponent, I have to make it into a fraction. So the cube root of 27 can also be written as 1/3. So does the cube root of 27 equal 3? Yes, it does. So the solution to this problem, all the way over here, is that our exponent is 1/3. All right, so hopefully that gives you a starting point. I'm going to go ahead and pause the video at this point now, and we will come back to it for our second video. Let's clear off this screen, get into my mouse, and we are done. See you in video 2.